Alex, are you online? Is that on the web? So I thought I would just alert you to a website I found over by Google. I recommend it to you if you have trouble getting good documentation. So I think it has the second C in here. C++.com. And then you can do /ref, although I think if you just go to the basic website, it would be obvious what to do. But for instance, we have this statement that we keep seeing at the top of our programs, include, and then there's always a name like IOStream, I think, right? And then there's one called CMap. Have you found that one yet? Anyway, I personally was wondering where are all these things coming from and how do you find out each one? Like, how would you know if you're writing a new program, which one of these you need? So on this web page, there's a list of all the libraries. If you click on each library, it gives you a list of the functions that are inside of that library. Okay? So you can find out everything that's inside of CMap, everything inside of IOStream, anything you want to know. And then on each one of the functions, you can click on its name, and it shows you the syntax of how to use it, how to call it. So this is really useful, very good background material. My impression of the course materials that you have, all these recorded notes, they're very nicely put together, they're very organized, but there doesn't seem to be a single source that just has all the information that you can go look up. So if it doesn't already appear in one of the examples, I don't know how you would learn it. And this website, you can look up anything in C++ on this website. So maybe we can follow up. Okay, then a couple of questions from yesterday. First of all, let me ask you this. So did you figure out what the fastest computer in the world is? Who figured it out? Anybody? Not interested, huh? Maybe you could pretend you're interested. Okay, the fastest computer is called Fujitsu K. And guess how many flops it does? What is a flop? Floating points, operations per second. Okay? 8.162. So let's see here. If we put an M, that would be 1,000,000 megaflops. If we put a G for gigaflops, that would be 1,000,000. What comes after here? Terabyte. What comes after Terra? P is next. Okay, so that's 10 to the 15. This does 8.762 petaflops. That's fast. Okay, that's very fast. Now, all of these super fast computers, they can't achieve that speed on a single chip. What's the speed of the chip in your laptop? Yeah, who knows? The laptop gives the speed. If you buy it, it'll tell you what the chip is on the CPU. Yeah, it's usually something like this. So that's the speed you have on a single laptop. So the way that these computers usually achieve this kind of speed is that they're made up of literally thousands, maybe tens of thousands of CPUs like that. And they function in parallel. Right? Everybody knows the difference. This is a good computer concept. Parallel versus serial. So what does it mean to be serial? Well, they could be connected to each other in parallel also. Yeah, each thing comes after something else, one after another after another. Right? So let's say we did a program like this. Then I write x plus y, maybe I have c equals x plus y, and d is equal to y plus z. So this might be a normal sequence of commands that we might put into a C program, a C++ program. This is five commands, and it happens 5 in a row, the way that we write it. Now let's suppose we had multiple computers, and we had the connections all worked out, so they communicated very well with each other. This command, which normally would go second, does it depend on the outcome of the first one? No, it doesn't, right? Y equals 3 has nothing to do with x equals 2. So actually, these two couldn't be done at the exact same time. So if I had 2 processors, instead of having 5 commands, I can move this one over to the other processor. Now this one only has 4. How about z equals 4? Does it depend on those? No, it doesn't. So now if I have 3 computers, look how much faster we already made our computer. It used to have to do 5 statements in a row. Now it only has to do 3 in a row. So we're close to doubling the speed. All right, how about c equals x plus y? It depends on the output of these two, right? So it has to go over here, maybe stay where it is. How about d equal to y plus z? It doesn't depend on that one, but it does depend on those. So this one could move up. So now, in terms of the total amount of time, instead of taking 5 steps, in 2 steps I can calculate all 5 of these. But to do that, I need 3 computers to do it. So these super fast computers, this is what they have, is they have a logic that looks at the program and it figures out the maximum way of dividing out the work simultaneously. How can I possibly make this as simultaneous as possible? And it has, some of them have 30,000 CPUs. It's amazing, okay? Then what starts to limit the speed is literally the speed of light. Because to fit 30,000 CPUs takes some space. And the electronic signal going along the wire can't go faster than the speed of light. Nothing goes faster than the speed of light. So if it has to go back and forth between 30,000 CPUs, it's that amount of time, even as small as that time is, it starts to limit the overall speed, the communication of the speed. It's amazing. A lot of these big computers are water cooled. They generate a huge amount of power, and they need a lot of cooling, otherwise it's too hot. I was joking yesterday about smoke coming out of my laptop. Actually, for these computers, that's not a joke. This is a Japanese computer. There was a Chinese computer that used to be the fastest, and it changes once every month or 2 months or 3 months. Somebody comes out with a new one, just like everything else with computers. But the one before this one was Chinese. That Chinese computer used 4 megawatts of power. The Chinese computer used 4 megawatts of power. That's a lot of power. Right? That's a huge amount of heat. Almost all of that power gets turned into heat inside of the computer somewhere. So getting rid of that heat is a major challenge for computers. It's not a new idea. One of my classmates, when I was a student a long time ago, after we graduated, his first job was with a big computer company called Honeywell. Have you heard of Honeywell? And they were working on a water-cooled computer, just like a water-cooled car. It has a radiator full of water, and the core is all down inside of water. Water circulates all around, a nuclear reactor maybe, or a car, or whatever. Because water is a more efficient way of removing heat. Okay. All right. Anyway, so that was inside on the speed. One other thing I wanted to tell you, I think I mentioned maybe the 140 class, but let's talk about it in here in for a minute. So I have colleagues that I've worked with recently, and they're really hardcore computer scientists. And one thing they're excited about is simulating the human brain. So I think we talked about how the human brain is made up of a bunch of individual pieces called neurons. And each neuron has a certain logic to it that you could represent, for instance, with a relatively small C++ program. Right? So a chemical, an electrical signal comes in one end of the neuron, goes out the other end. If you connect enough neurons together and you duplicate the function of each neuron, you can duplicate the hardware of the human brain. And if you could duplicate the hardware of the human brain, then maybe you could download the human brain on a DVD or on a thumb drive, or even put it on an email. FileZilla, and you can send your brain over to wherever you feel like going today. I think I'll send my brain to South Africa today, look at some elephants. And tomorrow I think I'll go to the North Pole, look at polar bears. Anyway, so it turns out that I also discovered while I was looking for the fastest computer what the largest simulation of a human brain is so far, and it's equal to approximately 1/100 of the hardware of the human brain. Now, to give you an idea of just how complicated this is, 1/100th of a human brain, which, by the way, this is approximately equal to all of a rat brain. So this idea of building hardware to simulate the human brain, it may be more difficult for a human brain because it's bigger. But we've already built one that does 100% duplication of the hardware of a rat's brain. It's interesting. Okay, so how big is this? This is 1.6 billion neurons, and it has 9 trillion connections. 9 trillion connections. A trillion is like giga. I'm sorry, this is like tera. This is giga. 9 trillion connections out of 1.6 billion neurons. That means just the way that they're connected adds up to a total of 9 trillion places. So if you're truly trying to build the hardware of the human brain, this is only about 1/100th. And it gets more complicated because if you made another 1/100th, they don't just connect at one place. The number of connections would be even bigger than 2 times this. So it's an amazing challenge, but my colleagues in computer science tell me that we're going to do it. Okay, we had questions yesterday about N-L versus \n. Is everybody, are we up to speed on that, or do you want me to summarize one more time? Okay. Most of the time, L and slash N are mostly equal. The way they're used isn't quite the same, right? This must be inside of quotes. And this must not be. So a statement would look like C out in L. That statement, that's exactly equal to a statement that looks like this. C out. These two statements are exactly the same. Okay? And when do you use them? You use them when you want to go to the next line of output. So if you put this in or this in by itself, it will go from one line to the next line. If you want a blank space in between, then you should put two of these in. Okay? If you want two blank spaces, you can put three of them in. When you go to the next line, it automatically goes all the way to the left end of the next line and starts over. So if you had two C output statements, one of them said this and the next one said that, if you don't put those in, this will appear immediately after that. If you put one of these in, then this goes to the next line and they line up on the left side. Any questions about that? Yes? Yeah. You can put as many of them in as you want. Okay, so this statement is equal to this statement. Those two are equal, okay? But there's a lot of ways, right? Those two are also equal to this. That's also equal. Am I doing it the wrong way? I have a bad habit with that. I am doing this the wrong way. Yeah, keep me honest on that. Thanks. These are all the same. These will all do exactly the same thing. Now, the one place that's not quite the same is if you're writing or reading to a file. And not the computer. You need at the end. At the very end of all statements, of all C out statements, not each individual statement, just at the end of all of them, you must have an end out. Okay? Does everybody understand what that means? So in other words, in your whole program, all the way through the whole program, you can use either end L or /n, whichever one you choose. If you're doing C out and C in, it never matters. But if you're reading and writing to a file, which was part of, I think, 2.4 or 2.5, 2.4, right? So you read 2.4 for today. If you're going to read and write to a file, then at the very end of the last read statement or write statement, you do have to use end L, not /n. Okay. End L is the trigger that tells the computer finally to go ahead and write to that file. All right, what else? Somebody asked about reading from more than one line, or reading more than one variable in one line. That's fine. This statement, these two put together are exactly the same as this. These are exactly the same. Okay. If you put in more than one variable in a command, it has to have a space in between them. Now you can generate the spaces by tab. Does everybody know what the tab key does on your computer? Yeah, you can set the width of the tab. That's completely up to you to adjust. And if you hit tab, then it always goes over however far it has to go, so that you get the straight columns and numbers. Now, I think if you're typing it in on screen, if you're really using CN, probably the tab isn't so important. But if you're doing reading from a file, my opinion is the tab is a really nice thing to use when you create the file you're reading from. Right? Let's say you want to put a bunch of numbers inside of a file. So maybe it's a data file, data.txt. I think it's nice if you use tabs. So you can put a 1, and then if you hit the tab key, and let's say you have the tab set for column 10, then 2, and then you go to the next line and you put 3. If you hit tab, it goes directly to that spot. And then you put 10, and then you can go to the next line, you can type in 127, you hit tab, it goes right to here, you can put 5. And the nice thing is these numbers are all lined up. Instead of being kind of random left to right, you get a nice column of numbers, another nice column of numbers, and so on. So in my opinion, your input file will be much easier to read and to manage if you use the tab. Otherwise, it's completely up to you, of course. Yeah, Excel usually always looks like this. Excel has a tab delimited output function. Okay? It's called tab delimited. I don't know, it's a crazy word. It's some word that a computer programmer made up. I don't think it's really English. I'm not sure what it is. When we haven't done Excel in here officially yet, but when we do Excel, you may want to generate a big input file. And if you use the output, what's it called, export function from Excel, you can export it into a text file that's tab delimited. And that will put the numbers in nice, even columns that makes it easy to read. Okay, what else? Necessary off-stream. Okay, so OF stream, IF stream, is everybody okay with that? There are certainly lots of useful programs that involve reading and writing from the computer screen. However, a lot of engineering, the data files that you want to use are just too big. You're not going to sit there and type them in over and over again. The data itself gets generated some other way, and the file is huge. So this input-output from file, this is really important. Another thing that can happen is once you start looking around, if you're interested, you'll find that there's a lot of data available for downloading. Okay, like for instance, in the U.S. government, I just worked the last 2 years for our National Science Foundation. It's the highest science research organization in the U.S. It sponsors a lot of basic science research. There's a rule that if you get funding from this agency to do science research, you have to make your results publicly available. So you can go to the website, maybe somebody's measuring ocean temperatures, right? Maybe you're interested in global warming and you want to see what the ocean temperatures are. You can go to the website and download the data file, but it may have millions of numbers in it. Okay, so it's really important to be able to manage this reading and writing the file business. You can download the telemetry data for satellites. Has anybody ever gone outside and watched satellites fly overhead at night? I think it's kind of fun. It's an amazing thing. You know, if the sky is reasonably dark, you have to get outside of the city usually. But if you get to a place where the sky is dark and clear, the sun shines on the satellite, and even though the satellite's not very big, it reflects the sunlight so bright that you can see the satellite fly overhead. It's pretty awesome. But they can be hard to find the first time. Once you see it, you can still keep watching it, but to find it the first time isn't always very easy. Well, a lot of satellite orbits, the data is available online. You can go download the data. You'll know exactly when it's going to fly over. Okay? You know, airplanes, I mean, you can think of an ATM. He gave the example of ATMs. I mean, probably none of us use the ATM often enough that it really matters, so our files wouldn't be that huge. But anything like that, any kind of big piece of information, lots of numbers, you don't want to have to type it in. So it's really good to know how to read and write from a file. And now that we're learning about the control blocks, if else, do, while, etc., right? Everybody's becoming expert on that. So we can use our own C++ program to generate a huge amount of data. So again, we want to write it to a file. We don't necessarily want to write it on the computer screen. Okay, good. Alex. Sorry to wake you up. Could we look at lecture 2.4 for a minute? While Alex is looking for that, let me ask you this question. The EAS 140 class is not going to meet tomorrow, so the morning time is open if you want. I propose that we meet tomorrow morning and not tomorrow afternoon. How about that? Is there anybody that can't do that? Is that okay? I mean, everybody is supposed to also be in the 140 class, so it shouldn't be a conflict. You should have that time available. Okay, so tomorrow this class will meet at 9 o'clock tomorrow. Okay, and we don't meet in the afternoon. You can do whatever you like with the afternoon. Okay. Yeah, and maybe just skip to slide number 6. Yeah, just put the right arrow key. Oh, that's okay. Okay, good. Yeah, I don't think I must have written down the wrong note. I'm sorry, slide 16. I said 6, I mean 16. I think that's the last one, or close to the last one. Okay. Does anybody have any questions about this example? Did everybody look closely at each line and did it make sense to you why it does what it says it does? There's mixes inside of here. There's mixes of /n inside. There's indel. Some reading and writing from the input and output. Right? When you get to name your device, that's kind of cool. So you can call an input stream and give it whatever name you want. And then whenever you use that name, it's like you've defined a new function. That's sort of like the read command that puts those numbers in. Another thing this example uses, we talked about the difference between the computer doing the arithmetic and algebra that actually doesn't make any sense. So here's another example where the algebra, if you just look at the pure algebra, it doesn't really make sense. And that's this statement. So this program is calculating the average of 6 numbers, but it's only using 3 variables. So it reads the first 3 in, then it adds them together, so now it has the sum of 3. Then it reads in 3 new values, so this eliminates the first 3 values. It doesn't even remember them anymore. Then it adds those 3 to the previous sum, and that's how it gets the sum of 6. So it gets a total of 6 numbers, but it only uses 3 variables to do it. Okay? Now, again, the storage is not as much of an issue as it used to be, but I want to point that example out because that's really clever. You can do it with less than that. You can do it with a single variable. You could read the first number, add it to the sum, the variable called AVE, then read the second number over again in the first number location. Just call it A. And then add it to average. Then read A again. Now it's the third number. So the variable A gets used 6 times to read the numbers one at a time. And so you only use 1 storage location instead of 6 storage locations. Okay? Now, saving 5 storage locations is not a big deal. But maybe A has, maybe when we get to arrays, A represents 1 million ocean temperatures. So it's a lot of information. And storing it 1 time instead of storing it 6 times could be really important. It could make your program a lot more efficient. So I just wanted to point that out. Okay, let's go ahead and look at lecture 2.5. I think, let me pause for a minute. Any questions about 2.4? Oh, 2.3, that's okay.
In the slide, you said plus not equal and plus equal before. I don't understand what that's.
Yeah, good question. So, C++ has some commands you can use to add and subtract values, which I think, to me it's goofy. I don't think you need it, but yeah, this has the effect of setting k equal to k plus 1. It's the same thing. And I think, is it minus plus or minus? Minus k? Yeah, that's k equal to k minus 1. Yeah, k plus plus? Yeah, I don't know. I have to look those up. That website that I just erased that has all the documentation, that's the kind of place I think that is easier to find out.
Yeah, I think you can for example, unary example in the file.
Okay, can you open unary? Oh, you got it already. Oh, okay. Oh, okay, so before and after you so you don't understand what this part means?
Possibly plus but I understand for the plus character minus character.
Okay. So if you put, well, he's got an example here, right? So I equals 2 times k plus plus. All right, we start with k equal to 1. So what does this statement produce? So what would the value of I be when we evaluate this statement? 2, right? Because this comes after the k, so you use the value of k. This is after k has been utilized. So you utilize k first, and then you add 1. So at the end of the statement, I is equal to 2 and k is equal to 2. Okay? So this pair of statements is exactly equal to a pair of statements that says I is equal to 2 times k is equal to k plus 1. It's the exact same thing. If you put, does he have the other? He's got minus k. Minus k times 2. Okay, so in this example, what are they equal to? Minus k. So k is equal to k minus 1 before you use it. So you make the change to k first, then you use it.
So
So minus minus k reduces k by 1, so k is 0, and that means I is also 0. That's exactly equal to these two statements. That one would be the same, but now k equals k minus 1 first. These two statements are exactly equal to these two statements. My opinion. Who cares? I mean, write these two statements. C++, Fortran, all of these computer languages, all these higher level languages that have specialized functions in them, that I think the only reason they're in there is so that some computer programmers can be arrogant. Because it doesn't really add any logic. Everything you can do with this command, you can do with this pair of commands. There's no real advantage. It's just one more thing to try to remember. I think it's not worth it. Anyway.
How about the last one?
Okay, how about this one? So let's do this one. So we've got I equals plus k times k plus plus. All right, let's do I first. All right, so for plus k, you add 1 to k before you use it, right? So right here, this is k equals 2. And for k plus plus, you put k equal to k plus 1 after you use it. So for right here, it's still k equal to 2. But now you're going to add 1 to it after you use it. So the final value of k out here is 3. And the value of I is 4. Okay? It's like taking candy from a baby.
How about the last one? Why taking?
Just a second, I want to try. Have you heard this expression, taking candy from a baby? Okay, so there's a bunch of expressions in English. Most of them aren't very nice. But if something is supposed to be really easy, right? So if you see a baby who's got a piece of candy, it looks pretty good, it's easy to take it away from a baby because it's just a baby, right? So we say, this is really easy. This is like taking candy from a baby.
Really that easy.
Yeah, another one we say is, it's like catching fish in a barrel. So if you go to the river or the ocean and you try to catch a fish, it's not so easy. But if you just have a little barrel, the fish is in the barrel, it's pretty easy. So we can say it's like catching fish in a barrel. Okay. All right, so plus k, that changes, whoops, let me back up for a second. Plus k, you do this statement before you use k. So the first thing that happens here is we add 1 to k. That's why this becomes 2. This one, you also add 1 to k. That's why k ends up being 3. But you do it after you use it. So at the time that you use it inside the statement, it still has the value 2.
But it is, I think this one basically because k plus here after we use.
Yeah, this one it appears after we use it. But this one that happens before we use it.
So the last one should be for 1.
Let's write out the statements. This is equal to the first statement. The order of these statements would be k is equal to k plus 1, because this happens before we use it. But this happens after we use it. So the last statement is k is equal to k plus 1. This one comes from here. This one comes from here. In between those two, I is equal to k times k. So these three are equal to that. Exactly equal. That's how come I is 4 and k is 3. Okay, it's terrible. Why not just write this? It's logic though. I will say this, the computer, with all of these languages, there's one truth that you can't get around, and that is the computer can only be absolutely exactly right every time. Right? There's no argument. It's exactly what it says it is. So in this case, you add 1 to k before you use it. It has to be this. In this case, you add 1 to k after you use it. So it has to come after this statement where we actually use K. This is where we use K. Let me ask you this. What if, let's change the order. Now what do we get? Yeah. Yeah. What's K? Yeah. Okay, but I don't like guessing. I think you should know how to figure it out. So let's try it again. So with this order, right? What happens first? What happens first is we have to increase K by 1 before we use it in this side. So the first thing that happens is K is equal to 2 over here. The first statement is K is equal to K plus 1. A minute ago, that statement came because this one was over here, so I had the arrow like this, but now it's coming from over here. But at the same result, but it's coming from the other side. Then this statement is also going to add 1 to K. So that's why K is going to end up being 3. With this statement, it only adds 1 to K after we use K. So it comes up down here after we use K. And in the middle, we have to use K. And when we use K, I is equal to K times K. At this time, the value of K is 2. So it's exactly the same. Okay, let's try another one. Let's keep this is probably good practice, so let's do another one. Let's make it a minus minus here and see what happens. Here's a brief challenge for you. I'm going to count in my head to 20, and while I count in my head to 20, you figure out what is I and K. Okay.
What is K? K is 1.
Yeah, K is 1, and then this statement. Okay, so maybe we'll take a vote. I said the computer is always exactly right. Well, maybe we'll vote, and then whatever we vote, that's the answer, whether the computer likes it or not. And so, okay, so you think K is 0 and I is 0? I is 4. K equals 0, I equals 4.
I think I is 1.
Okay, just a second. How many people think this is right? Ouch. By yourself. Okay, what? K is 1 and I is 4. How many people like that answer? Wow, still not very many. 3. And you said it. You should hold your hand up. So 4.
I think I is 0.
Okay, what else?
I think I is 0 and K is I don't know K. I is 0. Don't know K. We don't know what is
Wait, you think I is 0, but you don't know what K is? How can you know what I is if you don't know what K is?
That's a K minus 1. So that is 1. K is 1.
Okay, so I equals 0, K equals 1. Who likes this set?
No. I equals 0, K equals 2.
Okay, so we have another quote. I equals 0, K equals 2. I have to tell you, I'm getting some ideas for a test question. We don't seem to have a very consistent idea here. So I equals 0, K equals 2. Who likes this answer? Alright, so I only count a total of 7 votes. There's a lot of people out there that didn't vote yet. What do you think the answer is? I equals 2. I equals 2, K equals 2. Who likes that answer? You like that? Bring it up. You got it. K equals 3. Okay, so we've got another one. I equals 2, K equals let's figure it out. First, let's do the easiest thing right now. When it's all over with, what is the value of k going to be? That should be easy. What happens when it's all over? Whether it happens before or after we actually utilize k in the statement, the effect here is to take one away, right? That's what minus minus means. It's either k. It's always k is equal to k minus 1. The only question is, when does it happen? But it happens some point in that statement. So this takes 1 away, and this adds 1 back. So the final answer for k is definitely 1. Okay, now there's a chance we got the right answer. Let's see if we got it. Okay, so k minus minus takes 1 away after we use k. But plus k adds 1 before we use it. So the first thing that happens is k is equal to k plus 1. So now k is equal to 2. Then we evaluate I. I is equal to 2 times 2. So it's 4. And then k is equal to k minus 1. And it's back to 1. So this is the right answer. And it also got the most votes. However, it only got 4 votes out of 1, 2, 3, 4, 5, 6, 7. Okay, it got 4 out of 33, so that's about what, 12%. So about 12% got the right answer. Not good. We want 100%. All right, let's try another one. How about this? No, I'm sorry, let's do it this way. Okay, what happens first? Plus k before it's utilized, right? So again, it's just the same thing I just had. Okay, is that different? Okay, before k is utilized, what happens? This happens first, right? So the first thing that happens is k is equal to k minus 1. So therefore k would be 0 at that time. The next thing that happens is I is equal to k times k. I is equal to 0. The last thing that happens is k is equal to k plus 1. K is back to 1. It's like catching fish in fairway. You know what? I think it might help you to remember this. If you, who thinks they understand this and who still thinks they're confused? Who's still confused by this? Okay, what I think will help you with the confusion is, remember what's going on in the hardware. So in the hardware, there's a place for I, there's a place for k, and there's a place for anything, any kind of intermediate calculation. So when the program starts, here's the spot for I, and here's the spot for k. Right? And we come down here and we get k equals 1. So in this hardware now, there's something stored for 1. Now it gets to this statement, and it has to evaluate the statement. The one that has the minus signs before, because it comes before k, that happens first. Before k is utilized. takes k out of the memory, and it subtracts 1. So now it puts it back over here, and now k is equal to 0. The next thing that happens is, it evaluates this expression. Why does that happen next? Because the plus plus only comes, k plus plus comes after. So now it evaluates this expression, and it takes 0, and it multiplies it by 0, and it writes 0 and I. Then the last thing that happens, after k is utilized, add 1. It takes 0 out, that's 1, puts it back in there. Okay? Yeah, that's an interesting, right? So what happens with this one? Great question. Whoops. Now what happens? Okay, so having the plus plus and minus minus after means we're not going to do anything to k until after we use it. So I, it's very obvious what I is. What's I? I is equal to 1. Now this adds 1 to k, this takes 1 away from k, so k is still 1.
What is the sentence there? You said one. So why is you plus 1 and minus 1? Two steps, right?
It is 2 steps.
That is one step. Because it's one.
It's all on, it happens, it tries to do it at the same time, but it has to do it sequentially within that one line. But it doesn't matter, right? It doesn't matter which order it does it. If it happens at the same, theoretically it happens at the same time.
So for the like you get pay the full after that pay from 1 and pay for 1, right?
Well, in theory, you could say that somewhere in the middle here, there's an instant when k is equal to 2. But it doesn't have any meaning because the 2 steps that go one after the other, no question, is to add 1 and subtract 1 from k. And there's no way to pause in the middle because both of these statements are already executed. So really, it never really stops at k equal to 2. In theory, it goes from k equal to 1 up to 2 back to 1. In theory, but it doesn't really do that because those two things happen at the same instant. So it's really just 1.
As long as the second instant simply go by the
Yeah, well, if you want to think of it as happening one after the other, I think that's okay. The final result is the same. Say that again. Say it one more time. The maximum line? Maximum for what do you mean? I just has one value. Put all 4 of them into one statement? Yeah, we can do that. That's good. Okay, what happens?
Stay.
What's the first thing that happens? The before statements, right? The befores go first. So here's 2 befores. 1 takes 1 away from k, but before anything else happens, this one puts 1 back in k. So k is still 1. Then I is equal to 1 times 1 times 1 times 1. So I is equal to 4. I'm sorry, 1. Then what happens? The after statements. Here's 1, it takes k from 1 to 2. This takes k from 2 to 1, but it happens at the same time, nothing else happens in the middle. So at the end, k is 1. Yeah, let's do this. Let's take, here's an idea. Maybe we're beating this to death, but here's an idea, right? You can take out, there's 4 pieces on here. So here's a real quick homework assignment. You have one, not homework, classwork, okay? You have 1 minute. Evaluate this product 4 times, but each time just take 1 out. So pretend that isn't there. What do you get? Pretend this isn't there. What do you get? Pretend this isn't there. What do you get? Pretend this isn't there. What do you get? Okay? I started off saying that I didn't think it was very important to know these commands, and I still think it's not that important to know these commands, but I think understanding how to evaluate the logic is critically important. If you want to be a good programmer, you have to understand the logic. So now I think this actually is good practice. So let's do it. Fun stuff. Okay, let's do the first one together, and then I'll pause in case you're confused, so you can work on the next one. So what is the value of I? Let's do K first. What's the value of K? Okay, I hear 1 and I hear 0. Anybody say something besides 0 or 1? Everybody agrees it's either 0 or 1 for K? Who thinks K is 0? Yeah, I've got mine too. Who thinks K is 1? Okay, K is 0. Why is K 0? K is the easy one in all these statements because the minus is always going to take 1 away, the plus is always going to add 1. Whether it happens first or last, before or after, it doesn't really matter.
We thought that you said about K before, and I thought that the first stage is to find K, and the first K is 0. The first K is, the first step, K is 1. I thought you were talking about that stage.
No, I mean at the very end of the statement.
Okay.
Yeah, so After the statement is over, the value of k is 0, and what is the value of I?
1.
You like 1? Who likes 1? Anybody like any other answer? Yeah, I think it's 1 too. Okay, try the next one. K is 2. Right. That's easy. What about 5? You like 0? And I heard 1. 0 and 1 for I. Anybody else? 8. Okay, what happens before we calculate I? K goes up 1 and then down 1. So at the time we calculate I, K is still 1. So I is 1. Then after we calculate I, K goes up 1 more. That's why K is 2. So in this one, before we calculate I, what happens? K goes up by 1. Right? So I is going to be 2. I'm sorry, that's 8. And after we calculate I, K goes up by 1 and down by 1. So K is going to stay 2. It's like catching fish in a barrel. Too easy. What about this one? Before we calculate I, K goes down to 0. Right? So I is 0. And after we calculate I, K goes up 1, down 1, so it stays at 0. Beautiful. You feel smarter? Alright, I'm glad we looked at this. I think, like I said, it's the logic of the if statements, the do, the while, you're asking a little bit earlier, that can be really confusing. So I think it helps to do this exercise. Even though it's not directly related to if statements, it is a good exercise of logic. Okay, why don't we look at 2.5? That was a 2.3 question, right? You have a question for 2.1? 2.4, again. Yeah, is there one, is there an example that we can look at, or do you want me to write it? Any noted example? 5, 6? Okay, so what's the name of one? Can you tell me exactly? Example 12? Page 12 in lecture 24? Yeah, okay, so page 12, Alex? Yeah, so what exactly is the question? Yeah, you can put any word you want here, and that becomes the name of the command that you're going to use to write. The only word you can't put in there is one that already exists as a function inside of a program. Yeah, and this is part of the include, okay? Because, for instance, there's a function inside of CMath. Inside of CMath, there's the function called sine. Right? I keep using that example. But inside of library CMath, CMath.h has most of the normal math functions that you're used to. So somewhere inside of there is the thing called sine. So if you had include CMath here, then the name sign would already be defined as the function that means the sinusoid. But because it's not included here, you could, if you wanted, name your file sign. That would be okay. You can use any name you want as long as C++ isn't already using the same name. My advice is make up a name that's your name that has nothing to do. Like it would be, I think it would be a mistake to use a name like that because you'll just make yourself confused. Even if you wanted to, let's say that the output, let's say you're writing a program and you're going to put a bunch of sinusoids in as the output, go ahead and write out the words like this. Or maybe even call it sinusoid output. Give it some name that's obviously your name, not from the program. Then you won't be confused later. Okay? Okay, any questions about this? Looking ahead for a minute, 2.8, section 2.8, did anybody look at lecture 2.8 yet? I didn't ask you to, but maybe you wanted to look at it yourself. You don't have it? Oh, you have 2.5, right? You don't have 2.5 yet? Oh, that's not good. Okay. Shoot. Okay, well I'm going to go over at the beginning of 2.5 anyway, myself. Then maybe somebody can come by the apartment, I'll give the thumb drive and then just lectures on it. So for next time then, 2.5, 6, 7, and 8. Now that looks like a lot, but these three are actually related to each other. And this one actually is related to 2.4. I'm not sure why they're put in the order they are. But let me just tell you what's in 2.8. So for reading and writing, right now we only know a couple of ways to control the appearance of the output. In fact, I think we really only know maybe two things. We could do this, and we could put some label in. So we know how to write a word, and then we could have the value itself. But when it prints the value, we don't know what it's going to look like. Probably it's going to look like 6 digits with a decimal point somewhere, but maybe it'll have an exponent. We don't really know. So in 2.8, what you learn is a lot of commands that enable you to make the output look however you want. So I think I asked before, how many of you used Excel? Has everybody used Excel? No, not nearly everybody. Okay. Well, then I want to use that as an example. Just as one example, I think in the U.S., when we do our money, it's customary to always put 2 digits to the right of the decimal point, because this is for dollars here, and then our smallest unit of a dollar is 1/100. We call it a cent. So if you're going to write a U.S. money, you put say 125. That's $1.25. There's nothing in between 24, 25, or 26. We don't have any half cents. So if I were writing a program, and the point of the program is to calculate money, it would be nice if when I print the output, I print the output in exactly this form, because that's what everybody's used to seeing when they see money. If it comes out and it looks like this, that doesn't look like money, because there is nothing, this has no meaning when we're talking about U.S. currency. So that's one example of controlling the format. Another example of controlling the format is putting it in different places sideways across the page. So we have this command, we have this command, and we know that those will move down one line, but we don't really have any command for moving backwards and forwards sideways. So I'm just giving a couple of examples, but the point of section 2.8, the idea of 2.8 is to enable you to write much fancier output files. Okay? So I think if you want, you could skip straight from 2.4 to 2.8 now, and then you could read it because you just read about output in 2.4, then go back and do these 3 in a row. Now I'm going to talk about 2.5. Okay? Any questions? We started a little bit about 2.5 last time with the do loops and the end loops. So the basic structure is to have an if, and then if else. And then you can have multiple if else. And finally at the bottom you have else. Right? Each one of these are separate commands. Now, else doesn't have any kind of qualifier on it, but the first three, they all have qualifiers. You don't have to have these in here either, but I'll talk about it. So, inside of here, we put some kind of logical, which is sometimes called Boolean expression. And these expressions have only two possible values. What are they? True or false? It's either true or it's false. So then you can have an open bracket and a closed bracket, and you can put as much C++ in here as you want. You can have a whole program inside of there. Same thing here, open and closed. Put as much as you want. Same thing here. Same thing here. So this is the structure. Now, all of the if-else statements, you can have as many as you like. Actually, I'm not sure that's true. There might be some upper limit. Maybe you can't have more than 100 or something. I don't know what it is, but there's not a reasonably low limit. It's a big number. And I'll tell you in just a minute why you might want to use them, but you don't have to use anything with it. You could have just the if and just the else. Or you could have if, else, or you could have or, like I'm showing. And what the difference is, the reason why you would use one instead of the other, depends on how many possible outcomes you're interested in for the logic of the program that you're trying to do. So let me give you an example of, this is one you're going to see in your notes. It's for mixing paint. So there's three primary colors, red, blue, green. No, not green. What is it? Is that right? Is it green? RGB. Yeah. No, this is yellow. It's yellow, right? Yeah. Okay. I think these are the three primary colors. Right. So. You think it is green? How do I get yellow if it's green? I think I get green from blue and yellow, right?
The RGB colors are red, green, and blue. I don't know how they mix it.
Yeah, I agree with you. I mean, it's often called RGB, yes. Red, green, blue. But I don't think green is actually the greatest color. I think it's yellow. So now I wonder why it's called RGB.
I think from a painter's standpoint, it's yellow.
Okay. Okay, so if we combine these two, what do we get? If I combine these two, what do I get? Blue and yellow. It's green. How about red and yellow? Orange. Which one did we do? Is there a combination we didn't do? I think that's all of them, right? Okay. All right, so let's suppose we're going to write a program and we want to know if we put two colors in, what color is going to come out. Okay. So our first statement could say if, I'm going to write in words right now. This isn't the code. This is the idea. Okay. If color 1 is equal to blue. Now, this statement has to be written in the correct syntax, which we'll do in a minute. But for now, the idea is, if this thing is true, then what the computer does next is this stuff. If this is not true, if it's false, what the computer does next is this statement. This statement also has to have a logic. So let's say color 1 for this logic. Color 1 is equal to red. If that's true, then the computer does this logic. If that's not true, it goes to this statement. Color 1 equals, what we say it was? Yellow. Green. Okay? If this is true, it executes these statements. If this is not true, it goes to this statement, and it checks it. If this is true, it executes these statements. If this is not true, it goes here. If this is true, it executes these statements. If this is not true, it goes down here. Okay? If this is true, and it executes these statements, when it's done, it goes here. If this is true, it executes these statements, when it's done, it goes here. So everything above the else command, no matter how many if-elses you have, only one of those sets is going to get executed. The first one that turns out to be true is the set that gets executed. So if one of them is true, when that's all done, it comes to else. And if none of them are true, it comes to else anyway. Yes?
Why do we have to put the false logical expression? Because we can think about the right one.
Yeah, but let's say that you have you're writing a computer program so that somebody who doesn't know what they're doing can try mixing different colors and see what happens. All right?
We write our own program.
Yeah, you write your own program. So let's start. Let's see. I'm just going to do this for the top part of the C++ program. So let's write some logic. Let's say we're going to do character, and we'll say C1. C2, all right? That stands for color 1, color 2. So the idea of this program is the user will put in two colors, and the program will tell them, if you mix these two together, what do you get? That's logic, okay? So now we want to read Cn from C1 and C2. How long is a character variable? No. A character variable in C++ is one character. Okay? So C1 is going to store one character. C2 is going to store one character. Okay? So let's put in instructions. First I'm going to do a C output. Input, color 1 and color 2. Okay, so that'll appear on the screen, and then the person types their two colors. Now, we want to make our first comparison. So let me take this out. And we'll say if C1. Now this is the symbol inside of C++. A double equal sign. That means I'm going to check to see if it's equal. C1 is equal to. I want to check against a character. And now let's assume that the person, if they type in red, the C1 will only store one variable. Character only stores one character. So the thing it would store would be R. That would be the first character it sees. So if C1 is equal to R, so if the first color they typed in is red, then what's going to happen is it's going to execute these commands. Any questions about that? Now, let's write this logic. There's two possibilities under red. One is that the second color was blue, and the other one is the second color was yellow. Two different outcomes. this if, as part of these statements, I can begin with if C2 equals blue.
So why do we have to equal sign?
That's the syntax for a comparison, right? If I put one equal sign, what happens? One equal sign assigns the value on the right to the name on the left. This means A is equal to 3. I'm telling, in this statement, I tell the computer A is equal to 3. Okay, so I need a different symbol to show the computer the difference. This symbol means I'm telling the computer A is equal to 3. This symbol means I'm asking the computer, is A equal to 3? Okay? So this statement has two possible outcomes, true or false. If A is equal to 3, this statement is true. If A is not equal to 3, the statement is false. This statement has only one outcome, A is equal to 3. This is a command. This is a question. Okay? Is that clear? Okay, so that was the beginning of the logic. Now the next logic is to check the second color. If C2 is equal to B, if that's true, then it means the first color was red and the second color was blue. So now what I can do is write right here, C output. Let me go ahead and swipe these away. Red and blue would give me purple, right? So C output. Your color is purple. Okay. Or the other possibility, so I'll click else. Else means the second color must be yellow. If I mix red and yellow, the output should be orange. C output. Your color is orange. Yeah, you can have more ifs, more else's. You can put in a lot of different. You can make this as big as you want. It depends on how patient you are. Okay. Yeah.
If I input 2R, it's been
2 R's. Yeah.
C1, C2 is red.
I guess that would be an example of trying to make your program idiot proof. Because the point of the program is to mix two different colors and see what you get. So if you put in two of the same color, but yeah, we could put that statement in. We could check that, right? We could say this. We could put a statement in that says, if C1, right? That would be a check to see if somebody put in the same color. And if they did, we could write a statement like this. You are an idiot. Okay? Why not?
So I can fix that if after the else or I will insert an if from another if C2 is equal to the
Yeah, you mean, why don't I have this statement in here?
C2.
Yeah, see, I don't need it. I could put that in, but I don't need it at this point. Right? I don't think I need it. But actually, you're right in a sense, because this program, the way we wrote it now, it doesn't check to see if C2 is a valid color. So let's think of what could happen. Somebody puts in for the first color red. So we come to this statement, and this statement turns out to be true. C1 is equal to red. Yes, that's correct. Now we go here, we check to see if the next color is blue. If they put in blue, the mix is purple. That's also correct. But this logic doesn't actually check to see if it's not blue, is it yellow? This logic just assumes if this is false, if it's not blue, it must be yellow. And so therefore your color is orange. But actually that's not true, right? Somebody might put in a different color that's not red, blue, or yellow. So maybe we would want to have one of those. So let's write a statement that would check to see if C1 is red, yellow, or blue, and if C2 is red, yellow, or blue. So I'm going to give you a new symbol here. So if C1 equals red, and now I've got to think about the symbol. I think it's this one. I'm going to put another bracket here. So I'm giving you a new symbol. It's 2 vertical bars. Okay. C1 equals blue. C1 equals yellow. Yeah, that's okay. So, yeah, then what would we do? So this statement would go at the top of the whole program. And then down below this one would be an else. And the else would say, you entered a bad color. So let's go through this line by line. I'll tell you what it means, okay? You gave a bad input. Okay, this symbol right here is the logical OR. What does a logical OR mean? By the way, in C++, there's a total of 9 logical statements. We'll go through them in a minute. I'll list them all, okay? So the first logical check is, are 2 things equal to each other? That's what this check is. All right, let me say them all real quick. So that's one. Another logical check would be, you can ask if one thing is bigger than another thing. You can ask if one thing is greater than or equal to. You can have them both. It can be either greater than or equal to. You can have less than. You can have less than or equal to. Okay? You can also ask if 2 things are not equal to each other. You don't have to ask if they're equal. You could ask if they're not equal. Then there are these combination statements that are if and, they're or and they're and. Okay? How does that work? If I have 2 variables, if I have 2 logic statements, each one of which could be true or false. If there's an and in the middle, it becomes one logic statement, and both have to be true in order for it to be true. If and is in the middle. If or is in the middle, one has to be true for it to be true. Okay? So what happens over here, this statement I just wrote? Is C1 equal to red? That could be false. But this says or, is C1 equal to blue? That could also be false. Or, is C1 equal to yellow? That could be true. If that's true, the whole statement is true. Because this is or and this is or. Anytime you compare 2 things and they're both or, only one has to be true in order for it to be true. So if I say today is Wednesday or Thursday, that's true. It's Thursday. If I say today is Thursday or Sunday, it's true. If I say today is Monday or Wednesday or Tuesday or Thursday, or it's true. Right? As long as I have Thursday in there, it's true. Even if everything else is false, if Thursday's in there, it's a true statement. But if I say and, today is Wednesday and Thursday, it's not true. Because today's Thursday, that's true, but it's not Wednesday. So it's not true that it's Wednesday and Thursday. If I say today, right now, it's Thursday and it's afternoon, true.
So if I say 1 plus 1 equals 2 or 3, so that's true or false?
Yeah, if you say 1 plus 1 equals 2 or 3, that's true. That's true. If you say 1 plus 1 equals 2 and 1 plus 1 equals 3, that's false. But if you say 1 plus 1 equals 2 or 1 plus 1 equals 3, that's true.
theory applied.
It's still true. This is the idea of Boolean logic. So, yeah, it's true in English, it's true in general English language as well. But it's definitely true on the computer. Yeah, there's and there's or. Else is what happens if something is false. Okay, so let's start from the top. All right. Let me do a sequential thing from the top. So the first kind of thing you can check. All right, I'd like everybody to be quiet for a minute. Really tune into this for a minute. I'm going to go through this one more time. Make sure that you understand each different piece of logic because it's all different. Okay? But it's all based on the same rules. So you have to understand the same underlying rule. If there's a logic statement in there, it has only two possible values. It's binary, right? It's like 0 or 1. But we use the names true or false. If C1 is equal to R, that's either true or false. It either is equal to R or it's not equal to R. One or the other. It can't be both. Okay? So, this statement is true. If C1 is equal to R, it's false if it's not equal to R. If this statement is true, it executes everything that's inside of these blocks. Inside of these blocks, I start the logic over again. If this statement is true, do that. If it's not true, do this. That's what the else means. And here, the same thing. If this is not true, it skips down. It could go all the way to else, except I put this other if else. This has precedence. So now it comes here and evaluates this statement. If that's true, it does this. So that's the logic of evaluating what happens, what's inside of here is true or false. But what's inside of here can be a lot more complicated than one simple question, like, is C1 equal to R? I can have in there multiple questions, and if they're connected by an and, everything that's connected by and has to be true in order for the whole thing to be true. If it's connected by or, at least one has to be true for the whole thing to be true. All right, so what's my statement in here? I have three questions in here. My first question is C1 equal to R? My second question is C1 equal to B? My third question is C1 equal to yellow? As long as one of those three things is true, this statement is true. But if one of them is false, if all three of them are false, this statement is false. So that's where the you are an idiot comes in, right? Because if these are all false, if the first color is not red, not blue, not yellow, then you didn't put in the right input. So that would be the output. Right? You're an idiot. Well, this is a different version, right? This is saying C1 equal to C2. If you put in two of the same colors, you're also an idiot. Any questions about that? Yeah, you can put in as many of these logic branching. We talked about branching last time. You can put in as much branching as you like. There's no limit. Yeah, branching. Branching means that you're going to evaluate the statement to see if it's true or false. And if it's true, one thing is going to happen. And if it's not true, another thing is going to happen. That's the idea of a branch. You know what a branch is on a tree? You start at the bottom, you start at the ground on a tree, and there's one trunk. But then a branch goes off, and off of that goes other branches. So the idea of branching is when I get to this point, I have to make a decision. Do I keep going this way, or do I go this way? So that's a logic decision. Go this way or that way. So what these if statements tell me is which way I'm going. If this is true, I'm going this way. If it's not true, I'm going down here. It's just like this branch. But inside of each of these, after I make the first decision, I can have more branches. Right? So let's say this is true, that represents going out on a branch. So this is true, so okay, I'm going this way. Now I get to another place where I have to decide, am I going that way or this way? There's another if statement buried inside. These things can be buried as deep as you want to bury them. The branches can be incredibly complex. You may not realize it, but the programs that you're using on a daily basis are just absolutely full of these branching statements. Think about how many times you can put an input into a program you're using, like, I don't know, maybe your mail program, and it does something automatically based on what you put in. You know, you can click reply. Actually, every menu is a bunch of branching statements. Every submenu. When you go into a submenu like File, you click on that, you get a submenu. There's Save, Open, New, I can't remember them all. You tell me. Save As, Close. Right? There's a whole bunch of them. So what happens when you click on one of these? When you click on one of these, the computer is reading that as an input. It's going into logic exactly like this. And if it says, did she click close? And if she did, then here's the logic that closes the computer program. If that's false, it goes to the next one. If else, did she click save? If you did, it does something else. But if you didn't click save, it goes to the next one. Did she click new? If you did, it does this. If not, did she click save as? The computer's just full of branches. Thousands of branches. Somebody said, we were talking a little bit after the first class, I forget who it was, but I'll just point out, who was saying that? I should remember that. Anyway, if you look at the size of one of your C++ statements, right? Take one C++ statement, like, I don't know, like this one. Type it into a .txt file, see how big that file is. It's probably 5K or 10K. How big is Microsoft Windows? How big is Windows XP? I think it's something like 2 gigabytes, right?
It's 500 megabytes.
500 megabytes? Okay, only 500 megabytes. All right, so one statement is 5 or 10K. So 1,000 statements would be 5 megabytes. Right? 500 megabytes would be 500,000 statements. So it's not a perfect correlation, but that gives you some idea. Microsoft Windows might have 500,000 commands in there. Think of how many branches there are. Because inside of Microsoft Windows, you have so many choices. You can do this, you can do that, you can do the other thing. When you click on one, what happens? Somewhere underneath there, somebody like you wrote a bunch of logic like this. So if you click on this button, one thing happens, and if you click on another button, another thing happens. Clicking on those buttons is the same as typing in the input, R, Y, B. They just made it easy for you, so you don't have to type save. You can just click on the word save. Right? Think about that. You've got one of the things that we already have seen we have some trouble with is if we ask somebody to type an input number and they put it in the wrong format, our computer doesn't know what to do with it. Right? So Microsoft beat that problem. They accomplished that problem by not letting you type the input in. You don't get to type it. It doesn't ask you to type save or open or do. It doesn't ask you for that. It gives you the buttons. You can only click one button. That way it knows exactly what you mean. It's not like you can misspell it or something like that. It's just one button. Yes? Sorry, were you saying? Okay, so this logic, you'll see in 2.5, 2.6, 2.7, there's a lot of different logic. So this is the if else logic. There's logic called do. There's logic called do while. I'm trying to think of what else there is. There's for. All of these are ways of creating the branches. They're all ways of creating branches. Are we finding something? And all of the branching decisions are based on these logic statements. And here, let's do a couple of quick practices of logic. Is that true or false? Okay, what does this mean? look in pieces. Let's do these two first. False or false? What's the outcome? False. Okay? Now, true or false? What's the outcome? True. Okay, so the output of that statement is true. All right, let's put another one. Let's add some. What's that? It has to be either true or false. Okay, so let's try another. Let's say true and true. I don't remember the symbol for and off the top of my head. I know this is the symbol for false. Okay, so what would be the outcome of that statement? It's true. Okay. What's the outcome of this part? This is false. If the word and is in there, both parts have to be true in order for it to be true. If the word or is in there, either one part or both parts have to be true. So the outcome of this side is also true because it's and, but both sides are true. And then true or false, the outcome of the or, if one side is true, that's true. Okay. You had homework on the pyramid volume. Have you done the exercise yet where you convert the volume into inches or feet? Okay, well it's coming. You'll see that. So you'll have some multiple logic to do. What it asks you to do is the following. It's not a bad idea. When you go to calculate the volume of the pyramid, depending on what size the base and the height you put in, you may get a really big volume or a little very small volume. So the units that you use to calculate it should probably be adjusted so that the number doesn't look silly. Right? Like let's say you use units of meters, but your cylinder is this big. So the volume of this in meters is probably 1/1000 or 1/10,000 or something like that. So it would make more sense to report the volume of this maybe in millimeters cubed or in centimeters cubed instead of meters cubed. So you put logic in, you put the logic in that says, if my number is less than or equal to, say, 10, and greater than or equal to 1, then I like it. I like a number between 1 and 10. If it's not, the end of this statement, this is so good, you could say this is the end. Let's write it the other way then. Let's say if the number is less than 1, or the number is greater than 10. That means the same thing. Right? This means exactly the same thing as asking, is the number less than 10 and greater than 1? This logic, this mathematical logic is exactly like and. This means number has to be between 1 and 10 for it to be true. It has to be both. It has to be both less than 10 and bigger than 1. Otherwise, it's not true. This logic says, if it's less than 1, or it's greater than 10. Right? Yeah, sorry, this should be, if number is greater than 1. No, sorry, so this, yeah, this would, if this is false, if this is false, it means the same thing. So this false is the same as this true. Yeah. Okay. Now you can put this logic in there, and then you could do it one at a time first. So instead of checking both things at one time, you say if my number is less than 1, and now the logic inside of here says let the number be equal to the number times 10. Right? raise it by 10, and then let the unit go up by 1, whatever that is. So if the unit used to be millimeters, now it's centimeters, or whatever, you redefine it. Then you will want to circle back up and try it again. Because maybe the number was 0.01. So multiplying by 10 brings it up to 0.1, but it's still not bigger than 1. So you'd like to go through this logic more than one time. That's where the while statement comes in. Okay, so you do while,